Welcome to The Explainer. Today, we're plugging into a genuinely disruptive piece of engineering. We're talking about a completely unique, world-first approach to industrial filtration developed by MINETEK Technology. And I mean it when I say, literally, nobody in the world has created anything quite like this. If you work anywhere near fluid dynamics, manufacturing, or heavy industry, you know the drill. Filtration is just this endless, wildly expensive battle against physics. But what if we completely flip the script? What if we approach separation not with physical barriers, but with pure kinetic energy and gravity? Seriously, buckle up, because we're looking at a system that effectively eliminates consumable parts altogether.
Just think about that for a second. The massive economic drain in industrial operations. It isn't always the big machinery. Usually, it's that constant, bleeding operational expense, the OPEX, of replacing wearable parts. Filters clog, they tear, they fail. Machine downtime absolutely skyrockets. But what if a filter had zero wearable parts? What if it cleaned itself mechanically and lasted essentially forever? That's the exact promise of the technology we're breaking down today.
Okay, let's dive right into this. Here's our system diagnostic sequence for today. 1. Traditional flaws. 2. Enter the vibration filter. 3. The physics of separation. 4. Calculating filter efficiency. And 5. The economic advantage.
Let's kick things off with Section 1, Traditional Flaws, and the problem with the status quo. To really appreciate why MINETEK is such a massive breakthrough, we've got to look at why the status quo is, well, fundamentally broken. Traditional filtration basically forces problems through a very narrow set of solutions. Think about your standard mesh filter, right? Manufacturers claim a 10 micrometer mesh catches 10 micrometer particles. Sounds great. But what about a long, narrow metal shaving? If it hits that mesh head-on, it just slips right through, totally bypassing your defenses and potentially destroying some very expensive downstream pumps. Now, centrifuges try to solve this by spinning the fluid, but they consume just massive amounts of energy to generate artificial gravity. And flotation? By aerating fluids to float particles to the top, you're introducing air into hydraulic systems. That is an absolute engineering nightmare. It makes the fluid compressible, which causes violent, unpredictable system jerks, and worse, aerating combustible mineral oil? Yeah, that's practically a fire hazard. We desperately need a better way.
Which brings us to Section 2, Enter the vibration filter, a world-first design.
Now, what's really interesting here is this radical departure from traditional methods. This design completely abandons physical mesh screens and forced aeration. And this elegance didn't just appear overnight. It's actually the culmination of a 50-year scientific school founded by academician of the Academy of Engineering Sciences of Ukraine, Vladimir Kolot, and continued by Doctor of Technical Sciences, Professor Alexander Kolot. So, looking at the architecture, fluid enters through the inlet pipe on the left, you'll see it marked as number 2, and flows horizontally between a stack of tightly spaced, vibrating shelf plates marked as number 8. As the fluid travels across these plates, gravity just takes over. Heavy particles sink to the lower collection chamber through slit 11, while the lighter particles float up to the top collection chamber through slit 10. But the real magic here? It's exactly how this system creates the vibration that makes all of this possible.
Take a look at these kinetic mechanism components. Notice anything missing? There are no external electric motors driving this vibration. None. Instead, as the fluid flows in, the pressure of the fluid itself forces a free-floating striker ball, that's number 4, out of its static position. This ball begins rapidly striking a mediator plate positioned directly above it. This mediator is rigidly attached to the rack holding those shelf plates, so the kinetic energy of the incoming fluid is converted directly into mechanical vibration across the entire plate assembly. It's just a brilliant, self-sustaining kinetic loop.
Let's move on to Section 3, the physics of separation, and how we're controlling those forces.
Okay, but why does vibrating fluid between metal plates actually clean it so effectively? To understand that, we need to geek out for a second on the core science and math. Imagine a single microscopic sphere of dirt suspended in liquid. It's subject to 3 vector forces. F1 is gravity, literally just pulling it downward. F2 is Archimedes' buoyancy, pushing it upward. And as gravity starts to win and that particle begins to sink, it encounters F3, Stokes' drag. That's basically the resistance or the friction of the fluid itself pushing back up.
At a certain point, as that particle accelerates downward, the drag force F3 increases, until the upward forces perfectly balance the downward force of gravity. So F1 equals F2 plus F3. This equation represents the exact moment the particle stops accelerating and hits a constant, maximum falling speed, its terminal velocity. Now, in a traditional giant settling tank, this process is agonizingly slow, right? Because the particle has to sink through meters of resistant fluid just to finally reach the bottom.
So the crucial point is this.
In a standard tank, a particle might literally have to fall 3 meters to be removed from the flow. But in the MINETEK filter, the fluid is sliced into dozens or even hundreds of super thin horizontal layers between the shelf plates. A particle doesn't need to fall 3 meters, it only needs to fall the microscopic gap distance, denoted here as S, to hit the plate below it and be captured. By drastically reducing that required fall distance, you are exponentially speeding up the separation process.
But wait, remember, these plates are vibrating violently thanks to that striker ball. Why? Well, think about wet concrete for a second. If you drop a heavy steel block on wet concrete, it just sits there. But if you plunge a concrete vibrator into the mix, the concrete suddenly acts like water and the heavy block sinks instantly. That's exactly what's happening here. The kinetic energy from the vibration effectively destroys the fluid's instantaneous viscosity. Its internal resistance just drops massively. By applying this to the liquid in the filter, Stokes' drag plummets, and those particles settle at absolutely incredible speeds.
Let's check out Section 4, Calculating Filter Efficiency, or as I like to call it, the mathematical proof.
Because in industrial engineering, bold claims require hard, undeniable numbers. So let's look at the math. Over on the left, we've got equation 9. That's your classic terminal velocity depending on those vast, slow settling tanks we talked about. But on the right, MINETEK's engineers adapted this into equation 15, which brilliantly factors in the flow rate, the kinetic viscosity, and crucially, the dimensions and the number of gaps in their shelf filter. This equation actually lets us calculate D, the exact minimum diameter of particles that are mathematically guaranteed to be fully removed from the fluid.
Let's run a real-world scenario through that equation to see what happens. Imagine a super compact filtration unit. The shelf plates are just 1/2 meter by 1/2 meter. Inside, there are 167 shelf gaps. We pump water through this unit at an impressive flow rate of 350 liters per minute. The system footprint is tiny. We're talking no more than a 1 cubic meter box. So what does equation 15 tell us we can actually achieve with this setup?
100%. According to the literal laws of physics, at 350 liters per minute, this compact unit will perfectly and completely remove all sand density particles that are 14.6 micrometers and larger. The manufacturer conservatively rates it for complete removal of particles down to roughly 10 to 15 microns. And get this, that calculation doesn't even fully factor in the massive efficiency boost provided by the active vibration we just talked about. It is a totally stunning result for a filter that uses absolutely no physical mesh.
Finally, Section 5. The economic advantage. The bottom line.
At the end of the day, brilliant physics really only matters if it drastically improves your balance sheet, right? When you compare the lifetime value, the contrast is just undeniable. Classic filters lock you into a constant cycle of OPEX. You're buying endless replacement consumables, paying for labor to change them, and bleeding money through machine downtime. The MINETEK system, on the other hand, guarantees an immediate, unprecedented high economic effect. It's built from solid stainless steel, handles highly aggressive environments, purges sludge automatically, and has absolutely zero consumable parts to replace. Zero. It's a true financial revolution for the industry.
By leveraging gravity, fluid dynamics, and kinetic energy, MINETEK hasn't just improved on the mesh filter, they've basically made it obsolete. So, as we wrap up this explainer, I want to leave you with a pretty provocative thought. If a system can guarantee microscopic separation with zero wearable parts and zero replacement costs, is it finally time for your industry to permanently retire the replaceable filter? Thanks for plugging in with me today, and keep questioning the status quo.